Yeah, hello everyone. This is now the follow-up talk to the previous one. It's the same project, but now from the CT and DCT side. Why are we doing all of this? If we check the regulations, for example, IAEA 26, for their approval, we need a proof that no crack initiation at all happens at a specified temperature, for example, at -40 degrees C. And for nuclear transport and storage containers, this is at the moment done via high effort and very expensive drop tests. We see two examples here. And those are made from ductile cast iron. And for ductile cast iron, we have the big problem that there is no real validated method to assess the fracture toughness values. And the goal of the project is now to establish such a method. This is now, thanks to the previous talk, a quick repetition to refresh the mind. What's the master curve? Basically, we have to do a very small amount of tests. And with this small amount of tests, we can then do an evaluation of the reference temperature T0. And with this reference temperature, we get then this graph here. And the reference temperature T0 is here, the big bold line in the middle. And the master curve concept is then valid for the temperature of plus 50 degrees around this reference temperature, which are then this area. It's currently already used for the safety assessment in the nuclear safety department for pressure vessels, for example, as supplement to the ASME reference concept. And what's so good about it? Well, if we check it, for example, with the method in the ASME code, we only do 4 tests, but in the end, we only get a single value for the fracture toughness. And in the master curve, we only have to do 2 more tests, 6 in totals. And we get this whole temperature range from -90 to +10 degree, for example. So with just 2 more tests, we get a whole lot more to work with. For the project, we first need the material. We procured one. We've specially made one with a specification from our partner, Berlin. And we did 20 of those casting blocks with a mass of about, 12 DCI blocks with a mass about around 20 tons. And we cut each into 2 parts, which are about the size of those big SEB 140 specimens we have just saw in the previous talk. And further, after the testing of the SEB 140, we have extracted more specimens from those broken halves of those specimens, mostly the smaller SEBs and CT specimens. This slide we all have already seen. On our side at MPA Stuttgart, we are mainly doing the Pellini testing and the CT testing. The Pellini testing is already done. My colleague already mentioned it. We have performed the tests and determined a value for T NDT of -5 degree, which is quite close to the -5.2 we got from the Sharpie tests. Then we performed the CT testings. Currently, the CT25 testing is done. We used a machine which can go as fast as 10 meters per second and up to a load of 100 kilonewton. We used high-speed cameras at 100,000 FPS to measure the COD of the specimen. And for the force measurement, we used, for the slower tests, piezo loading cell. And for the faster tests, we used strain gauges. We tested at 2 different loading rates. One of the loading rates was 5 times 10 to the power of 3, and the other one was 5 times 10 to the power of 4. I will from now on reference those as the slower and the fasting loading rate. And after we have done our tests, we got these force COD curves here. and a lot of them showed pop-ins. And according to the standard, we have now to evaluate these pop-ins if they are significant or not. In this case, this one would be deemed significant, which means we have to evaluate the test at the point where the pop-in happened. Then we have done this evaluation for all of the curves. We performed the evaluation according to the standard, and then we got our KJC dynamic values, which are shown here. And our preliminary T0 values led us to this master curve. And those tests are now for minus 40 degrees. And we see those master curves are not a perfect fit, which is to be expected because not only the temperature is playing a role in the ductile to brittle transition range, but also the loading rate. So different loading rates should lead to a little different master curve. And now we just have to test at more temperatures, and those fit beautifully into those tolerance bounds. And then we are done with our project, right? Well, we did just that. Reality isn't that nice. As we can see, the additional tests don't really fit into those tolerance bounds we just have evaluated via the standard. This means for at least this data set of CT25 specimens, the master curve is not applicable as is, but that's what we kind of expected from the start. We have to do some modifications to it to apply it to ductile cast iron. And from now on, since our data set is not yet concluded, we are still waiting from the on the CT50 and the DCT9 results. It's a bit of a more open discussion because the results are just not yet final, so take it with a grain of salt now. For example, what we can do is, it fits quite nicely, this factor 0.019 is for the slope of the master curve. If we fiddle with that a little bit, I don't even quantify it because it's yet work in progress, but we can see we get a way better fit. Especially here, even the small scatter at minus 60 degrees still fits quite well into the tolerance bounds. Yeah, but we see it's still not yet perfect. So it's just one first modification attempt. It's to be expected. We see, for example, that here at minus 20 degree, the tolerance bounds are still quite conservative compared to the test results. For the faster loading rate, it's way better. And we also see at the slower loading rate, we have really high KJC dynamic values already at minus 20 degrees. While this is at a faster loading rate, this is not yet the case. So we did some SEM analysis because we spotted some black areas at those minus 20 degree specimens for the slower loading rate, which we can see here. The red arrow should be quite visible, those black spots. And under the SEM, we noticed that those black spots are just huge clusters of graphite particles. Our strain gauges for the crack detection also said we had a little bit of ductile crack propagation before the brittle crack initiated. So currently our theory is that we have here at the bottom, the pre-cracking, then a little bit of ductile crack propagation, and then the ductile fracture. That is the brittle fracture, sorry. And here at the brittle fracture, the crack just goes through the material, through the matrix, and just opens up those graphite particles which are in its way. While for the ductile fracture, the crack goes the path of lowest energy and goes from particle to particle, resulting in this very populated space because every single graphite particle is visible. That's the current theory. As I said, we are still working on more tests. With more tests, we can validate the stuff or change it. Which brings me to my summary and the outlook. As I said, we want to establish a method with which we can assess the safety of ductile cast iron in the brittle to ductile transition range. And for that, we have performed first master curve analyses with a lot of tests. And now it's planned to do the CT50 and DCT9 test series with 40 each specimens each. And currently for CT50, 20 of those are already performed. And we also plan to do finite element analysis of selected tests and further fractography and statistical analysis. And then we will see at the end if the master curve works for ductile cast iron or not. Thank you for your attention.